It's a cold, moonless night with a mist that hangs heavy in the air. As you turn to cross the road, fog swallows both the sound and headlights of the oncoming car. You see it too late and brace yourself for impact. Then, out of nowhere, an elderly stranger shoves you out of harm's way, is hit by the car, and ends up in a heap on the tarmac. Their life ends as yours is saved. Later, a police officer hands you an envelope found in the pocket of the deceased. It is addressed to you. You open this envelope and find a note with 2 words scribbled on it. It simply reads, "Study physics." Whoever wrote this note saved your life at the expense of theirs, so it only seems fair you follow their advice. Decades later, you become a much celebrated physics professor. Your specialist subject, Albert Einstein's theories of relativity. You've always had a hunch that time travel is possible, and one day, finally, you crack it, and the world's very first time machine is sat, buzzing before you. Only then does the penny drop. How had you never realized before? You now have the power to go anywhere and any when, but you know exactly what you have to do. You take the letter you've kept all these years out of its frame on the wall, place it back inside its original envelope, and put the envelope in your pocket. Stepping into your time machine, you set the controls to take you back to a cold, moonless, misty night, arriving just in time to push your younger self out of the path of the onrushing car. You die on the roadside. It seems simple enough. But the real joy of time travel stories like this one comes once you begin to scratch beneath the surface, and some incredibly profound questions begin to emerge. First of all, who wrote the letter? The older version of you simply takes the letter they'd already been given as a teenager back in time. The letter is a seemingly creatorless entity stuck in a time loop. This is the bootstrap paradox. Secondly, do these time loops keep on repeating? You save your teenage self, so they grow up to travel back in time to save their teenage self, who grows up to travel back in time, and so on. You are stuck in a relentless cycle of living and dying. But the letter isn't. Does it just keep getting older and more worn and tattered? This is the restoration paradox. And whose idea was it to study physics anyway? The notion seems to appear out of nowhere, a thought with no origin. This is the ex nihilo paradox. And if events like this can actually happen, then it also appears you have no free will, no choices in life. You were always going to invent the time machine and had absolutely no option to do otherwise. It had to happen, had always happened. If you don't invent a time machine, then you can't save your teenage self, and you yourself would therefore die as a teenager. There is something in your future that's firmly fixed. This is the predestination paradox. And finally, what if you change your mind? Unfortunately, for your older self, this is not an option. You can't get cold feet when you arrive and let the younger you get hit by the car. How could you be there to have second thoughts in the first place? This is the auto-infanticide paradox. It is impossible to kill a younger version of you, even through the act of not doing something. And so, not quite such a simple story. Welcome to the weird and wonderful world of time travel. But of course, traveling freely through time is impossible, you might say. You can't simply visit yesterday or rush headlong through millennia. And yet, this too is not quite so straightforward. Despite its myriad impracticalities, there are slivers of possibility lurking at the edge of physics, temporal loopholes lying just out of reach. And so, the question arises, if time travel were to be possible, just how could we do it? In 2021, a researcher at Portsmouth University calculated that there are about 6 × 10 to the power of 80 bits of information in the observable universe. That's a 6 followed by 80 zeros. Information is incredibly valuable and data brokers are collecting yours all the time. And that is where Incogni comes in, our sponsor today. They reach out to data brokers and help take your data off the market. You see, your data is being sold online without you even knowing about it, and even though you can reach out personally and ask for it to be removed, it could take years to do it manually. Luckily, Incogni have a fully automated system to do it for you, protecting you from data breaches that are becoming more and more common. In 2021 alone, they rose by 68%. Nobody likes being called or emailed by a stranger who knows your name and home address, so give Incogni a try to help protect your employment history, shopping habits, even the names of your relatives. This is the data that these brokers collect, and if it leaks, it leaves you at risk of fraud. So protect your privacy by following the link in the description. The first 100 people to use the code UNIVERSE will get 60% off Incogni. Thanks to Incogni for supporting educational content on YouTube. The sun beats down as the distinctive whooping barks of howler monkeys echo around the humid swamps. The current in the muddy, winding river is so strong that you don't even have to paddle your canoe. You just sit back and take in the sights and sounds as you're carried along. Jack Finney, arguably one of the finest proponents of time travel fiction, compared our experience of time to a river like this one. It seems like we're relentlessly ferried downstream from the past to the future. We have no need to propel ourselves, but slowing down, speeding up, or turning around and heading back upstream doesn't seem possible either. But what happens to the parts of the river that we've left behind? Or in other words, where does yesterday go? It certainly seems as if it just disappears, yet making the same argument about an actual river would seem ludicrous. You're unlikely to accept that the riverbed is torn up and mysteriously vanishes just because you've disappeared around the next bend. The upstream parts of the river are still there, even if you aren't. In the same way, it seems as if tomorrow isn't real until it is, that somehow it magically appears once the curtain falls on today. But that would be like new water springing up to make the river of time longer only once you approach. Where would it come from? And so, over the years, scientists have revealed that time really is like that river, with its length already laid out in its entirety, from its source high in the foothills of the Big Bang to its estuary at the universe's eventual demise. The past, present and future existing alongside one another. Your great-great-great-grandchildren every bit as real as you are now. Your great-great-great-grandparents still alive and well, frolicking in the swells upstream in the vast river of time. Philosophers know this idea as eternalism. It's the opposite of presentism, which argues that only now exists and that the past is gone and the future yet to emerge. Debates between eternalist and presentist philosophers have raged since the days of ancient Greece. Indeed, the 4th century philosopher St. Augustine compared the present to a knife's edge, straddling the perceived past and an imagined future. But to a physicist, eternalism is known as the block universe theory and is based on Albert Einstein's much-lauded general relativity, one of the most successful theories in the history of science. In 1905, Einstein publishes the special theory of relativity. It does away with Isaac Newton's notion of absolute time. There is no universal clock that everyone can use to agree on when something happens. Instead, as the name suggests, time is relative. Depending on how they move through space, one observer could see event A happen before event B, while another sees event B occur before event A. Both observers are equally correct. An event in your past could be in someone else's future. This is yet another reason why all our yesterdays cannot simply vanish. How can they, when the events they contain might form part of somebody else's tomorrows? As well as this, special relativity cemented the fact that space and time are not completely distinct from one another. In 1908, Hermann Minkowski develops Einstein's work and properly unites space and time once and for all. He says that moving through space affects how you measure time, because the 3 dimensions of space and one of time are actually woven together into a single fabric that he called space-time. But how do we know that space and time are actually bundled up together into the space-time that the block universe is made of? Proof would eventually come in tests of Einstein's general theory of relativity, which he presented to the world in 1915. Back in the 1840s, astronomers had harnessed Newtonian gravity to discover an entirely new planet. Using Newton's equations to predict the future path of Uranus, they had found that it appeared to deviate from that path. The French astronomer Urbain Le Verrier pored over the equations for months, searching for an answer. Was Newtonian gravity wrong after all? Not quite. Le Verrier suggested that an unseen, more distant planet pulls on Uranus and affects its orbit. If correct, Newton's laws of gravity would be vindicated, and in 1846, Neptune was found. Despite this success, and although he didn't know it yet, Le Verrier was about to hammer the first nail into Newtonian gravity's coffin. Planets don't have circular orbits, but slightly changing elliptical ones, with the Sun offset from the center. Newtonian physics claimed that these slightly changing orbits was due to the gravitational pull of the other planets, and Newton's equations were correct in their predictions for all of them, except one: Mercury. Le Verrier realized this in 1859, and the search began for another new planet, but no such world was ever found. Instead, the answer came from Einstein. On the 18th of November 1915, he wrote a letter to the German mathematician David Hilbert. Today I am presenting a paper in which I derive out of general relativity the perihelion motion of Mercury, discovered by Le Verrier. No gravitation theory had achieved this until now. Imagine the fabric of space-time as the surface of a trampoline. If you place something heavy in the center, it will sag in the middle. Likewise, the presence of a massive object like the Sun creates a dip in the fabric of space-time. Physicists call this a gravity well. Einstein was arguing that there is no Newtonian gravitational pull at all. It is merely a mirage. As the innermost planet, Mercury moves more deeply into the Sun's gravity well than its neighbors. The deeper it goes, the more the local space-time becomes curved, and it's this increased curvature that causes Mercury's orbit to change. For all the other planets, the curvature is subtle enough that Newtonian gravity gives the same answer. Only in the extreme gravitational environment that Mercury inhabits does Newtonian gravity show itself for what it really is: a good approximation. Gravity is not a pull. It's the result of curved space-time. Since then, astronomers have tested this idea in myriad ways, from solar eclipses to swirling black holes and rippling gravitational waves. And in every experiment, space-time passes with flying colors. Our entire cosmos of past, present, and future, merely a 4-dimensional block of malleable space-time that just sits there. A supernatural being that could somehow look upon it from the outside world would clearly see yesterday, today, and tomorrow happily coexisting. But where did this all come from? As with everything else, scientists believe that the Big Bang birthed all of space-time. In other words, all of space and all of time. The regions of time we refer to as the past, the present, and the future are all there together in their entirety. And so it's as easy for two people to exist then and now as they do here and there. They can be separated by centuries of time, just as they can be separated by kilometers of distance. Any object within this block universe can be given 4 coordinates. 3 spatial to say exactly where it is, and 1 temporal to say exactly when it is. Imagine that an object's location in the block is marked by a dot. Even the dot of a physically stationary object moves because its time coordinate is constantly changing as second ticks after second, and today relentlessly becomes tomorrow. Join all the dots belonging to one particle, and you have a line that maps out its path through the block universe. A world line. You are nothing but a collection of particle world lines woven together, a knot in space-time, shedding and absorbing new world lines as you move towards the day the knot that is you undoes itself, or is undone. All the actions you will ever take, from what you'll have for breakfast every day, to if and who you'll marry, and the houses and jobs you'll flip between, are all entirely mapped out. You can't deviate from your journey any more than a train can deviate from its tracks. In this way, the block universe is like a book. The beginning, the middle, and the end are already written and unchangeable. Every choice you think you're making is actually pre-written, and so one that you are always going to make. A character caught in a love triangle on page 150 may be unaware that it gets resolved 50 pages later. But resolved it will be, and in the way it was always going to be. And this is why our time traveler from the opening story had to invent the time machine. An older version of them had already indelibly appeared on an earlier page. Their world lines eventually looped back round to intersect with themselves at a previous point. But can this really happen? Can you travel to the seemingly long-distant past, or indeed the far-flung future? If over then is no different to over there, it seems that the door to time travel is well and truly open. In a distant corner of the universe, a gargantuan supermassive black hole is holding sway over an entire galaxy. Its intense gravity is pulling, stretching, and ripping up whole solar systems. Hot gas and dust whirl around it as its huge magnetic field spins up and spits out shrapnel into the void. Among this debris is a tiny subatomic bullet, a proton, which races across the cosmos as close to the speed of light as it's practically possible to get. It has 100 quintillion times more energy than an ordinary particle of light, and after traveling over 1 billion light-years, it slams into Earth's atmosphere with 21 million times the energy of collisions inside the famed Large Hadron Collider at CERN. It is so energetic that to this day, astronomers know it as the "Oh my God" particle. An example of an ultra-high energy cosmic ray, it is a reminder that the Earth sits in a celestial shooting gallery, and when rays like this one strike our atmosphere, the impact is so violent that it bursts into an invisible fireworks display of subatomic particles. Pions, muons, and neutrinos erupt and cascade down to the ground. In fact, cosmic rays are so plentiful that they give you an annual dose of radiation equivalent to 3 chest X-rays. And for one Italian physicist, cosmic rays became an obsession. His groundbreaking work on the muons created by cosmic rays, producing some of the first evidence that time travel to the future is not only possible, but commonplace. And his name was Bruno Rossi. Rossi is behind the wheel of an old bus, snaking along the highest road in the world where pine trees compete with snow-capped mountains to reach the sky. Eventually, he arrives at the place he's driven over 1,000 miles from Chicago to reach, Echo Lake. Nestled high up in the Mount Evans wilderness of Colorado, part of the world-famous Rocky Mountains, it sits almost 2,300 meters above sea level. Up in the mountains, Rossi is measuring the muons created by cosmic rays. Muons are unstable particles, and so they quickly break down or decay. Physicists call the time it takes for half of a group of muons to make this change their half-life. It is just 1.56 millionths of a second. But Rossi's measurements reveal something curious. Far more muons are reaching the ground than there should be. Even though the muons are traveling at more than 98% of the speed of light, over 15 half-lives should still elapse by the time they make it down to Echo Lake. With each successive half-life removing 50% of the remaining muon population, just 0.1% should reach Rossi. And so how come he is able to detect significantly more than that? The remarkable answer was that the muons were time-traveling into our future. Einstein's special theory of relativity says that you can think of anything moving through space-time as having a budget equal to the speed of light. The more of that budget you spend on moving fast through space, the less you spend on time. As the muons are traveling at close to the speed of light, considerably less time passes for them than for Rossi. From their perspective, fewer half-lives have elapsed, and so there simply hasn't been enough time for 99.9% of them to decay. This effect is called relativistic time dilation, and when Rossi factored it in, exactly the right number of muons reached the ground. But you may ask, does this really count as time travel? Imagine instead that you are the muon, but instead of traveling from the upper atmosphere to Echo Lake, you travel on a big loop around the universe at the same 98% of the speed of light and return home 25 years older. Those of us left on Earth will have been spending less of our space-time budget on speed than you, and so it will cost us more in time. But to us, you have spent your budget differently, foregoing time to travel through space. 25 years may have passed for you while you were gone, but 125 have elapsed on Earth. You have skipped forward a whole century. Indeed, such a journey could mess with the normal generational order of family relationships, as is poignantly explored in the short story Memories of My Mother by Ken Liu. And so time travel to the future is more than possible. We just have to accelerate humans to close to light speed. That is far from straightforward, however, because the faster you travel, the more energy you have. Einstein's famous equation E equals mc squared tells us that energy and mass are interchangeable, so if you gain energy, you also gain mass. In other words, the faster you travel, the heavier you get to an outside observer. A person traveling at 99.99% of the speed of light would weigh almost 2 tons, or about the same as a rhino. And accelerating them to that speed would require as much energy as everyone on Earth currently uses in 3 months. Understandably, we are very far from pulling that off, but even today, time dilation leads to some bizarre consequences. Take Mark and Scott Kelly, both former NASA astronauts who also happen to be twins. Mark was born 6 minutes before his brother. However, Scott has spent about 10 times longer in space, 520 days to Mark's 54 days. During these extra days, Scott was whizzing through space-time faster than his brother, spending more of his budget on speed and less on time. In other words, more time has passed for Mark than for Scott. Mark may have started out life 6 minutes older than his twin, but he is now 6 minutes and 5 milliseconds older. Had Scott been traveling as fast as a muon instead, their age gap would have widened to nearly 6.5 years, despite initially being born on the same day. And as if that weren't enough, there is another entirely separate form of experimentally verified time dilation, a second way to time travel into the future. Picture a clock, except this clock works differently to any you've seen hanging on a wall. It is simply made of 2 horizontal mirrors. A beam of light bounces between the 2 mirrors, and every time the light hits a mirror, the clock ticks. Let's imagine you have 2 identical copies of this clock. You set them running before taking one of them deep inside a gravity well, like the ones explored in the last section. Space-time is more curved inside a gravity well, and so the space-time between the clock's mirrors will also be curved. The beam of light will have no option but to follow this longer, curved path. In other words, the clock will now tick less frequently than the clock you've left behind far from the gravity well. Bring them back together, and more time will have elapsed on the clock that did not encounter the gravity well. But how can this be used to time travel into the future? Well, go and enter a deep gravity well and then return to Earth. More time will have passed on Earth than for you. You could hop forward a century, just as you did by traveling at close to the speed of light. However, to achieve a genuinely significant amount of time travel using this method, you'll need a very deep gravity well indeed, one far bigger than the Sun's. A supermassive black hole should do the trick as long as you're careful not to get sucked in. and just such a scenario was used as a key plot point in the film Interstellar, suggested by the famous physicist Kip Thorne. But Earth also creates its own gravity well in space-time. When Rossi drove his bus up the winding road to Mount Evans, he was moving further out of this well. In other words, he moved from a region where space-time was more curved to a region where it was less curved. He aged at a fractionally faster rate up the mountain than he did down the mountain. This difference is so tiny that a human is never going to notice, but atomic clocks do. The best are such good timekeepers that they are accurate to within a 15 billionth of a second every year. If you sync up two atomic clocks on the same shelf of a laboratory and then place them on shelves of different heights, they will noticeably drift out of time. Indeed, in 2022, physicists measured this gravitational time dilation using ultra-precise atomic clocks placed just a millimeter apart. And finally, you're likely to rely heavily on time dilation, probably without even realizing it. GPS has become an indispensable part of modern life for many of us. Our phones and cars can tell where they are on Earth thanks to an armada of satellites swarming around the planet. These satellites send out time-stamped signals, and the quicker you receive one, the nearer you must be to that satellite. In order to achieve this, the satellites carry atomic clocks, which are subject to both forms of time dilation. They are both moving through space-time faster than us and sit further outside Earth's gravity well. The time on the clocks has to be artificially altered in order to account for the fact that they are moving through time at a different rate to us. These experiments leave physicists in little doubt that time travel to the future is possible. It is established scientific fact. But what about heading in the other direction? Is it possible to head upstream and visit the past? It is 2011. Barack Obama is president, Prince William and Kate Middleton are newlyweds, and NASA's iconic space shuttle lands for the last time. In September, physicists make a shock announcement, one that rocks the scientific establishment. They seem to have observed particles called neutrinos traveling faster than the speed of light. If true, it would shatter one of the holiest doctrines in physics and open the door to backwards time travel. The bold claim comes from the Opera experiment buried deep under Italy's Gran Sasso mountain. Designed to detect neutrinos fired 730 kilometers through the Earth from CERN near Geneva in Switzerland, making that journey at the speed of light would take a mere 2.4 milliseconds. Yet some of the neutrinos appear to be taking 16 nanoseconds less than that. In other words, they seem to have gotten there traveling faster than the speed of light. Einstein's special theory of relativity says that the speed of light is an impenetrable barrier. The faster you travel, the heavier you get. The heavier you get, the more energy it takes to increase your speed further. Eventually, there comes a point when it requires an infinite amount of energy to increase your speed, so you can't. And that cutoff point is the speed of light. While a massless particle of light can travel at light speed, anything with mass cannot reach light speed, let alone exceed it. And so, inevitably, within a year the neutrino mystery was solved. The experimental equipment was faulty. The neutrinos weren't superluminal after all. The initial finding caused such a stir because traveling faster than light would allow you to travel backwards in time. And the story of why starts with a young Dutchman by the name of Willem Jacob van Stockum. In 1937, van Stockum publishes a paper with the seemingly dull title of The Gravitational Field of a Distribution of Particles Rotating About an Axis of Symmetry. While mundane in name, it was revolutionary in nature, for it showed that Einstein's equations allowed closed time-like curves in space-time. Our world lines usually stretch from the past to the future, but a closed time-like curve is a world line that doubles back on itself, closing a loop as it intersects the line at a previous point. A pensioner following such world lines could revisit the moment of their birth, or even save their teenage self from a car accident. Von Stockum had demonstrated that, at least on paper, there is nothing in the general theory of relativity to forbid backwards time travel, except that at first glance it seems bending your future world line into a closed time-like curve requires you to travel faster than the speed of light, to travel outside of what is known as your light cone. If your world line is the singular path that you actually take through the block universe, then your light cone represents all the paths that it would have been at least possible for you to take. Imagine that you are stationary in space, your world line moving forwards in a straight line through time only. What are your options for where you can go in the future? Well, assuming that we stick with special relativity, you are confined by the fact that nothing can travel faster than the speed of light, which is approximately 300,000 kilometers per second. 1 second from now, you cannot be more than 300,000 kilometers away from where you are currently. Yet you could be up to 600,000 kilometers away in 2 seconds, and 900,000 kilometers in 3. The further ahead in time you go, the bigger the region of space-time that your future world line is allowed to be in becomes. That's why it's called a light cone. The edges of the cone represent the furthest a beam of light can be from where it starts at any given point in space-time. And so unless you can travel faster than a beam of light, you are trapped within the same light cone, meaning that in order to loop your future world line around so that it intersects with itself at an earlier point, you would have to leave your light cone. In other words, time travel to the past appears impossible unless you can move faster than the speed of light. But there is another way to do it. If you constantly tilt your light cone so that your closed time-like curve to yesterday is always within it. And to do this, you would need to encounter space-time with an incredibly high amount of curvature. In 1974, the American physicist Frank Tipler explored this very situation, specifically what would happen to a cylinder containing at least 10 times the mass of the Sun and rotating along its longest axis. He showed that following a precise spiraling trajectory around this cylinder would warp your local space-time in such a way that your light cone would gradually tilt backwards. And as your world line must be somewhere within the cone, you would then be ferried from the present to the past. Visiting a Tipler cylinder and then journeying back to Earth would see you arrive before you left in the first place. However, in order to tackle the fiendishly difficult mathematics, Tipler had to assume that the cylinder is infinitely long. He couldn't conclusively prove that a shorter one would do the trick. It would also have to rotate billions of times a minute to warp spacetime enough. Hardly features of a practical time machine. Then, in the 1990s, Stephen Hawking added another layer of complexity. He argued that getting a Tipler cylinder that isn't infinitely long to work would also require huge amounts of negative energy. And it is here that quantum mechanics enters our story. One of the pillars of modern physics alongside Einstein's general theory of relativity, it deals with the subatomic world. According to quantum physics, even empty space isn't truly empty. Pairs of so-called virtual particles are popping in and out of existence all the time. Energy is borrowed from the vacuum to create them, taking the local energy just below zero in the same way that your bank balance drops into negative territory when you go into the overdraft and borrow money from the bank. Just like the bank, however, the universe eventually wants its money back. So negative energy is out there, but it's limited to tiny regions of space for fleetingly short amounts of time. As a result, closed time-like curves may exist in the subatomic realm, but creating a time loop big enough for a human to travel along to revisit the past seems an entirely different proposition. But there may be another way to achieve the same thing, a way to cheat the sacrosanct rule of the speed of light as the cosmic speed limit. A wormhole. In 1985, the celebrated astronomer, author and TV presenter Carl Sagan published a novel called Contact. In it, an advanced alien civilization reaches out to humanity with the design of a device capable of sending a single person across the vast chasm of space to the star Vega. Taking into account that nothing can go faster than light, this 25 light-year journey should take an extremely long time. So instead, Sagan wanted a way to get his heroine there far faster, but without invoking faster-than-light travel. Even though the book is finished, Sagan phones his friend Kip Thorne for advice. Sagan overnights the manuscript to Thorne, who reads it in the car the next day on his way to his daughter's graduation. A few quick calculations follow, and Thorne has the answer. What Sagan needed in his story is a wormhole. Imagine space-time as a sheet of paper, with the Earth at one end and Vega at the other. Now, instead of travelling the length of the paper, you fold the paper in half. After all, we know that space-time can be curved and bent. Earth and Vega are now right on top of each other. Hop the gap between them and you get there in no time at all. From the outside, it would look like you've got there by travelling faster than the speed of light. But at no point did you actually break through that sacred barrier. And so it follows that a wormhole can not only transport you to a different part of space, but it can also send you back in time. Let's say the wormhole to Vega is already set up. First, you need to attach the Earth mouth of the wormhole to a rocket and drag it round on a loop through the universe at close to the speed of light. As the wormhole has been spending more of its space-time budget on speed, less time will have elapsed from its perspective. This means that if you jump into the wormhole upon your return to Earth, you will emerge at the other end in the past. Crucially though, you will also be in the Vega star system. So it is backwards time travel, but not heading back into Earth's history. But there is still a way to pull that off too. Set the wormhole up in the right way and the time difference between its mouths will be greater than the time it will take you to return to Earth via the conventional route. You will arrive on Earth before you jumped into the wormhole in the first place. At least, that's the theory. In practice, it gets a little more complicated. Thorne realized that the gravitational pull of anything traveling through the wormhole will act to pull it shut. You would need something to help prop it open. This, again, could be negative energy, but physicists have also explored the possibility of using everything from quantum entanglement to magnetic fields. In 1985, J. Richard Gott and William Hiscox solved Einstein's equations for cosmic strings. 6 years later, Gott realized that they could also be used as a time machine. Just like spiraling around a Tipler cylinder, take the right path along cosmic strings, and you could end up tilting your light cone backwards. Quantum entanglement might be another option. Physicists know how to link two particles in such a way that changing one instantly changes the other, even if you separate them by huge distances. It's as if the information about the change you've made has travelled between the particles faster than the speed of light. But it has turned out to be impossible to actually transfer data superluminally using this method. So it seems there are multiple ways you might be able to travel backwards in time without breaking the light-speed barrier. But were it to be possible, what could you do about the paradoxes? Well, quantum theory might offer a solution there, too. The handcuffs dig into your wrists and sweat streams down your face as you stare at the table in front of you. On that table rests a glass vial of lethal gas next to a hammer on the end of a robotic arm. A robotic arm connected to a machine that is constantly measuring subatomic particles. These particles can be in one of two states, A or B, and the chance of measuring each outcome is 50-50. It's effectively a convoluted coin toss. If the outcome of the measurement is A, nothing happens. But if it is B, the hammer falls, the vial is shattered, and you die. The machine will make 100 measurements before the people watching from the other room will allow you to leave. Your odds of survival are around 1 in a million trillion trillion. You can feel your heart pounding in your chest as the machine makes its first measurement. A. You relax slightly, only to tense up again ahead of the next measurement a few seconds later. A again. After the 10th A in a row, you begin to feel hopeful. Surely you can't survive this. After 99 consecutive A's, you're practically giddy. It all comes down to one final measurement. The machine clicks. A. Your captors are true to their word and unlock the handcuffs. Although you don't know it yet, your unlikely survival against seemingly impossible odds just provided proof of the many worlds interpretation of quantum theory, with potentially important consequences for resolving time travel paradoxes. This is a human version of the famous Schrödinger's cat thought experiment. The original imagined victim was a feline in a box with the same vial of poison and hammer. Quantum physics says that instead of being in state A or state B, the particle is initially in both state A and state B at the same time, something physicists call a superposition of states. Except that means that the vial is also simultaneously unbroken and broken, and that the cat and you were both alive and dead until the point the next measurement is made. Is there something about actually making the measurement that forces the universe to finally choose one way or another? Not according to the many worlds interpretation of quantum theory. Brainchild of physicist Hugh Everett III, it says that every time there's an event in the quantum world that has more than one outcome, all outcomes happen. At that point, the universe fractures into two copies of itself. Outcome A happens in one, outcome B in the other. Reality is therefore constantly branching off to fashion a tree of possibilities. The great river of time bifurcates into infinitely many separate streams. There are some in which you were never born, and others where you are president of the Earth. If true, making 100 measurements with the poison and hammer machine would have created 100 different branches of reality. You died in 99 of them, and survived in one. As the sole surviving copy of yourself, you marvel at your own luck. The 99 copies of yourself in the other branches, though, aren't so fortuitous, covering a sliding scale from those who died after one measurement to those who went through the whole process only to die on the 100th. This is known as the quantum immortality experiment. There will always be a version of you that stubbornly refuses to die, no matter how many times the machine makes a measurement. In a sense, it's a game of Russian roulette that you can never lose. While physicists do not know whether this interpretation of quantum physics is the right one, the many worlds theory could help us resolve many of the paradoxes that are often associated with time travel to the past. Take, for example, the most famous paradox of all, the grandfather paradox. You use your time machine to go back and murder your grandfather as a child. However, that means he never reaches adulthood, never meets your grandmother, and so your own mother is never born. If your own mother was never born, then you weren't either, so how did you go back in time to murder your grandfather in the first place? Writers, philosophers, and scientists have come up with various ways to circumvent this issue. Stephen Hawking introduced what he called the chronology protection conjecture. It states that backwards time travel is simply impossible. The universe would act to rob you of any opportunity to go back in time. Cause and effect, sacrosanct, and tightly policed. Igor Novikov mused on something similar. His eponymous self-consistency principle says that you can go back in time, but that you can't change what's already happened. If you revisit an earlier page in the book of the block universe, you cannot rewrite what is already there. Attempt to murder your younger self, and you will fail. Maybe the gun jams, perhaps they sneeze and you miss. Try as you might, you could never succeed. This, of course, raises other problems, however, whether events in your future are predetermined, or even whether free will exists. Nor would Novikov's self-consistency principle work in all cases, as Barak Shoshani, Jared Wogan, and Jacob Hauser show in a series of papers published between 2020 and 2022. Imagine you have a working time machine. You also have a set of balls that are either black or white. Crucially, when two balls meet, the encounter changes their color, so a black ball becomes white and a white ball becomes black. Let's say a black ball travels through the time machine where it whacks into its past self. The encounter changes both balls to white. The collision also knocks the ball that's already time traveled onto a path that eventually sends it through the time machine a second time. In this scenario, the exact same ball exits the exact same time machine at the exact same moment in the past, and yet it is seemingly two different colors when it does so. This peculiar paradox cannot be explained away using Novikov's self-consistency principle. But according to Shoshani, Wogan, and Hauser, it can be explained using parallel time streams, the many worlds of quantum mechanics. They argue that time travel to the past is only possible if you emerge in a different stream from the one you left. So the black ball would start in time stream A, but would emerge from the time machine in time stream B. In this alternate time stream, it's the other ball that would end up going through the time machine after the collision instead, not the one that's been through once already. The ball that emerges from the time machine the first time is a different color from the one that emerges the second time. But that's now okay, because it is no longer the same ball. This kind of extreme mental gymnastics takes some time to wrap your head around, but it does offer a potential solution to the grandfather paradox. If you enter a separate time stream when you go back in time, then you can kill the version of your grandfather there, safe in the knowledge that the version of your grandfather that's crucial to your logical existence remains alive and well in the time stream you left behind. Your free will is restored, giving you the choice to do whatever you want. It is possible to use many worlds to circumvent the bootstrap paradox as well. In our tale of the time traveler saving their teenage self, the origin of the letter wasn't clear. No one seemed to write it, but perhaps we were missing characters from our story. The version of you in time stream A could write the letter, travel back in time to time stream B, and give it to their younger self. That teenager then chooses physics, grows up to invent the time machine, and travels back in time to time stream C to give their teenage self an apparently authorless letter. So we can also explain the bootstrap paradox away, but we need 3 versions of you existing in 3 separate time streams to do so. If that seems like using a sledgehammer to crack a nut, you're not alone. It could be a shining example of just how humans can tie themselves into intellectual knots. The number of splitting branches could be infinite. As the physicist Bryce DeWitt said, every quantum transition taking place in every star, in every galaxy, in every remote corner of the universe is splitting our local world on Earth into myriad copies of itself. But John Wheeler, the very man who coined the phrase wormhole in the first place, fell out of love with the idea. I have reluctantly had to give up my support of that point of view in the end, because I'm afraid it carries too great a load of metaphysical baggage. And yet, over the years, the many worlds interpretation has gained traction with physicists and now has a growing and loyal following. An endless array of views, each a little different from the next, playing out every possible outcome of every possible event in constantly fracturing streams along the great river of time. And so, as we travel along our world lines at varying speeds within the great block universe around us, time travel to the future isn't just possible, but has already been done, and is being done every day. Of course, traveling backwards is less clear, but it seems plausible, at least on paper, with a little helping hand from the counterintuitive world of quantum mechanics. For now, we'll just have to make do with the memories of yesteryear, safe in the knowledge that the past is very much still out there. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.